This video will show you how to perform a one-sample t-test in R. The dataset I'm going to use is the iris dataset. This dataset contains some basic measurements on 3 different species of iris flowers. And so I'll read in the dataset. In my next step, I'm just going to print the iris dataset to my screen so I can see all of the observations here. I have the length of the sepal, the width of the sepal, the length of the petal, the width of the petal for 3 different species of iris flowers. My next step is I'm only really interested in one species, in this case the Atossa species. And so I'm going to run this code that's just subsets all of the data to give me only the Atossa species observations. And so I'll run that. And you can see here in the upper right in the environment, it looks like I went from 150 observations for all of the observations to 50 observations for just the Atossa measurements. And so my task now is I want to perform a two-sided one-sample t-test. And my significance level is going to be 0.05. My null hypothesis is that the petal width for Atossa flowers is equal to 0.27 centimeters. And the alternative hypothesis is that the petal width for Atossa flowers is not equal to 0.27 centimeters. And then I want to talk about how I might interpret the results through the R code that I put in. That is, would I reject or would I fail to reject the null hypothesis? So to do this, we're going to use the t.test function in R. This will allow us to perform different kinds of t-tests. The first thing I put in is what measurements am I interested in testing? In my case, it's the petal width measurements from the Atossa dataset. And so I can write Atossa $ petal width to indicate I want to use those measurements in my t-test. I then put a comma, and then I put a value for what I want mu to be. In this case, I want mu to be equal to 0.27. That's what I'm testing against in my hypothesis. Are these Atossa flowers equal to 0.27 centimeters, or are they not equal to 0.27 centimeters? And the last thing is what I need to put is for the alternative. And this is really a statement we need to make for the alternative hypothesis. And in my case, I'm doing a two-sided hypothesis test. And so I can write eternal alternative equals 2.sided. So I'm going to click run, and we're going to see what kind of output we get. So you can see here, it says I performed a one-sample t-test. My data set was the petal width observations from the Atossa data set. The first value was it calculates the value of t. Now this is the value of the t statistic if we were to calculate this out by hand. So my value of t here is negative 1.61. And then it provides me the degrees of freedom. And in our case, this is always n-1 when we're performing a t-test. And that makes sense. We had 50 observations. Minus 1 gives us 49 degrees of freedom. And then it provides me the p-value. Perhaps one of the most interesting things we might do in a hypothesis test is to look at the p-value. And my p-value here is 0.1137. And then it spits out, it just kind of reframes the alternative hypothesis. So the alternative hypothesis is that the true mean is not equal to 0.27. And in our case, our units are centimeters. It also provides a 95% confidence interval, which might be of interest in our case. So this would be the confidence interval for petal widths from the Atossa data set. And then the last thing it provides me, it just provides me the average of X. So this is just the average of all petal widths in the Atossa data set. So how might I interpret these data and this output from the hypothesis test? Well, we can say that because we saw a p-value of 0.1137, this value is greater than the level of significance or alpha level of 0.05. Therefore, we can fail to reject the null hypothesis and conclude that the population mean for petal width is equal to 0.27 centimeters. So this is an important finding, and really the value in R doing t-tests is that it can allow us to give us the p-value that we could then compare to our level of significance or our alpha level.